Yeah, in this lecture we are going to talk about the applications of differential equations, like several major cases. We're going to focus on 4 special models. So what we're trying to do is the applications of differential equations. Applications of differential equations. So what we're trying to do is so let's say you have a real world problem. So real world problem. So what we can do, we're going to use some mathematical definitions, and we're going to create the corresponding mathematical model. So we're going to do the mathematical model. Okay. So we're going to use some abstraction, and then we're going to do the mathematical model. So this is the abstract. Okay, so you're going to get the mathematical model. So after you get to the mathematical model, what we're going to do, we're going to solve the mathematical model. Okay, so we're going to solve the mathematical model, and we're going to get a mathematical solution. So this is a mathematical solution. Now what we're going to do, sometimes this mathematical solution may not be understood by the general public. So what we want to do, we're going to interpret this again to the real world situation. So this is the interpretation part. So we're going to interpret it. So normally the physicist and then engineers gonna do that part. Okay, so that's their job. So you're going to interpret the mathematical solution to a real world situation. So this is how, like, normally we handle a problem in mathematics. So let's look at one major example. So let's say we can look at the what we normally call the exponential growth model. So exponential growth. So exponential growth model. So what is the exponential growth model means? So let's say for example, like these kind of things are like very common in nature. Like for example, when you want to make a bread or cake, or even like biology, they're gonna grow bacteria or some other cells. So so let's look at a situation like this. So let's say that's what we call the population exponential growth models. So let's say you have a disk, and then you're gonna put some bacteria in there. So this is a disk. So you put some bacteria, and if the conditions are good, what's gonna happen? It's gonna grow. This bacteria are gonna grow. So so these are some bacteria here. So let's say bacteria. So it's going to grow, if you let it grow, it's going to grow. So let's say P is the number of bacteria, or the population size. So let's say P equal the number of bacteria. Or sometimes what we call the population size. Okay, population size. So we can say population size. That's the number of bacteria. And then let's say T is the time. Okay, so you're going to measure the time. So T is the time. So then what's going to happen? You can see what is the rate of change that's going to grow. So what we notice is, if the population is large, the rate of change is higher. If the population is small, the rate of change is small. So that means one common mathematical argument is the rate of change. So the rate of change, is proportional to the population size. So that is a valid argument. So if you have a larger population, it grow faster. If you have a smaller population, it's going to grow smaller. So I mean that's the kind of danger in a like a situation like, for example, a virus disease, because when time goes on, how many you see a day gonna grow. Like for example, at the beginning you might see 3 to a day, but if you wait 3 months, you're gonna see 1,000 a day. So that's how it happened. The rate gonna change. Okay, that's what called exponential growth. So this is very common. So if you use the mathematical notation, what this means is the rate of change of the population growth, that means dp over dt, that's the rate of change, that's proportional to the population size. So in mathematics, if you have a proportion, you can always make it equality. So we can write this one as dp over dt equal the proportional constant times p. So that's the k is what we call the proportional constant. So if the population grow, is k gonna be positive. If the population gonna decay, what's the decay situation? Like for example, you know, the exponential decay, there's a nuclear material, and then it's gonna decay, it's gonna emit radiation, and it's gonna decay. So in that case, k is negative. So but this is a growth, so that means k is positive. So this is the growth. Okay, growth. It's gonna increase. It's gonna increase the growth. And then the question is, so this is the equation that we have. So the differential equation. Now the question is, you can see it's a differential equation because it has a derivative. It's a differential equation. So this is the differential equation for a exponential growth model. Now the question is how to solve it. Actually, you can solve this equation simply using your Calc 1 knowledge. Okay, so this is not a difficult problem. So let's see how we're going to solve it. So let's go to the next slide. So let's see how to solve it. How to solve. Okay, so this is like a very basic problem. So let's say, so we start with dp over dt equal kp. Now what we can do is you can change those terms here and there. So for example, we can write this one as if you consider dp over dt as a ratio, you can write this one as dp over, if you divide by p both sides, you're going to get that, and then I put k here and then move the dt to the other side. Okay, so this is how we normally like to solve this kind of differential equation. You move the terms around, you're going to move the p terms to one side and then the dt term to the other side. K you can put any side, but we normally put the k on the right side just to make it easy. Now what we're going to do, we're going to integrate both sides. Okay, so we're going to integrate both sides. So integrate both sides. So if you integrate both sides, what's going to happen? So let's integrate. So it is dp over p equal the integral of k dt. Okay, so integrate both sides. Now dp over p is like dx over x. Remember, like, you know, in Calc 1 we had that formula. So when you have dx over x, anyone remember what is the formula? Dx over x, there is a natural log, right? That's a natural log. So this is natural log x and plus c. So you have a constant there. So that's the formula. Dx of x, if you integrate that, you're going to get natural log absolute value x plus c. We're going to put the absolute sign there just to consider all the possible cases. So if you don't have that, it's only have one side. But here it has both sides. So it is like not just one side. It's when you have the absolute value sign, that means that's the positive side and the negative side. So that is the ln absolute value of x. Okay, so this is 1 and this is negative 1. So it has like a large domain, so it's much useful. Okay, it has a large domain, so that's the reason why we use it. So that is that. Okay, that's the graph of this function. There's both sides. Perfect. Okay, now let's go back to the problem. So what we're gonna do now, so we have that, and then we integrate. So that means if you integrate this one, what you're gonna get as in the other case is L natural log p absolute p equal, and then what's gonna happen in this side, this simply become k t plus a constant. Okay, because you integrate, a k is a constant, so you integrate dt means t, so you're gonna get that. Now what we're gonna do, you're gonna rewrite this one using exponential notation, because we know that some more mathematics, what we know about this. So if you you know that, like, if you have ln x equal y, this if and only if what, here the base is e, so right, the base is e. So what does that mean? That means this means x equal e to the y. So the y is the base. Okay, y is the base. So this is they are the same, but it's just another way to write it. This is exponential version, this is the exponential version, this is the log version. Okay, So this is like, you know, some result from college algebra. So we're going to use this result right now. So you can see that they can go back and forth. So we're going to get this. So if you use this result, so you can see on the left side now we have the log. So we're going to write the exponential form. That means if you use that, what's going to happen, you're going to get the absolute value p equal e to the kt plus c. Okay, e to the kt plus c. So now what we can do, we can write e to the kt plus c. We can write this one as what we can do, e to the c times e to the kt, because this is the exponential. You have a index, but you're going to add the index. So if you again go back to the algebra, we know that if you have x a plus b, which is equal to x to the a times x to the b. So that's what we use here. Okay, that's exactly what we use here. So if you have a sum, you can write this as a product. Now what's going to happen, we have the absolute sign. How to remove the absolute sign? See, it says the absolute value, because we know that the right side is always positive. That's having the absolute sign. But how to remove it? So let's look at again a similar situation. So let's say you have absolute value. If you have absolute value x equal to, what does that mean? If you have absolute value x equals to, what does that mean? This means something. If absolute x equal to, that means x can be either plus or minus 2. So you see that? So it's not just 1, but it can be, x can be the plus or minus. So we don't know. So that's the same thing happen here. So if you try to remove the absolute value sign, it's going to give you the plus or minus. It's going to give plus or minus. So the same argument works here. That means this one is p equal, if you remove the absolute sign, what's going to happen? Plus or minus comes here. E to the c, e to the kt. Okay, I hope it is clear now. The plus or minus comes because of you remove the absolute sign. Now there's something interesting. You can see that all these things, all these terms are, this is just a constant. The plus or minus e to the c is just a constant. Okay, just a constant. So I'm going to call that constant c again. So this is what we normally call the abuse of notation. Those two c's are not the same, but you can still use the same c because it's just a number. Just a number. So this is what we call by abuse of notation. By abuse of notation. Okay, so by the abuse of notation, you can just call that plus or minus e just c. Okay, but remember those two c's are different, but it doesn't matter. Just pick a c. So that means what's going to happen now is you're going to get your final answer now by pt. So we can write this as pt equal, I'm just called just c, just a constant, e to the kt. So that is the solution of the differential equation. You can see that it's not that difficult, just basic integration from calc 1. So you can just integrate these two. So you're going to change the terms to the two sides and integrate. Okay. So what happened now is if you try to graph this one, because we know that the k is positive, so that means if you try to graph this function, so what's going to happen, what it looks like, so it's gonna grow. Okay, it's gonna grow. So that means the solution looks like this. So what's gonna happen, it's gonna start with, see, if you plug in t equals 0, you get e to the k 0. E to the k 0 is 1. So that means when you plug in t equals 0, so you can see that p0 equals c e 0. That means c. That means at the beginning start with c value. Whatever the c value, you can start with that value, and then it's going to grow from there. It's going to grow exponentially. That's why we call exponential growth. It's going to grow exponentially. That means really fast. Okay, it's really fast. It's not the derivative is not constant here. So because if you take the derivative of this function, you can see that it is ck. So what's the derivative of this function? Derivative of this function is c is a constant, so k gonna comes out. So it is ck e to the t. So you can see that when time goes, this can increase. So it's going to go to infinity as t goes to infinity. So when time goes, this is going to grow really fast. Okay, so it's going to go really fast because that's the derivative, but that derivative increases really fast. See, there's e to the t is there, so that means the derivative increases. So that's what we call the exponential growth. Exponential growth is going to go really fast. Okay, exponential growth. It's not a constant. Okay, so not a constant. So this is going to increase. It's going to go to infinity. Actually, it's going to grow larger and larger and larger. So that's why, you know, in these kind of situations, like, you know, bacteria growth, a virus spread, those kind of situations, or like, you know, maybe someone spread a lie and then it's going to grow. So things like that. They all exponential growth. They all follow exponential growth, and it's going to go really fast. Okay. So yeah. So that's the time, and that's the PD. So once you understand the theory behind, you can really like very easily apply these things in practical situations. So that is one of the reasons why we want to kind of analyze these things and get a like fully understanding about this one. Okay, so I hope it's clear now. Okay, so this is what we call the exponential growth, and then also this solution is what we call the general solution. So this is the general solution. Okay, it's a general solution. So when you say general solution, it contains all the solutions. Okay, it contains all the solutions. So contains all solutions. Okay, contains all solutions. It contains all solutions. Okay, so so let's try to see this in a practical problem. So again, so what we have is here, if you have dp over dt equal kt, so if you start with this differential equation, and this is the solution we get. Okay, this is the solution we get. So you can remember this one because we can use this a lot. Good. So let's try to look at a situation where we use this idea. Okay. So how about this problem? So let's say, so example. So suppose there are 100 bacteria. There are 100 bacteria. Suppose there are 100 bacteria at time 0, okay, and 200 bacteria. Okay, 200 bacteria. Okay, 200 bacteria after 10 seconds. Okay, 10 seconds later. So the question is, how many bacteria? How many bacteria are there? How many bacteria will there be? After 1 minute? Okay, after 1 minute. So this is a situation. You're going to see that at the when you start the experiment, you're going to see. So we're going to start the experiment that means t equals 0. You're going to see that the population has 100 bacteria. Okay, and then you're going to wait 10 seconds. So when you wait 10 seconds, and then you're going to see that. So this is t equal 10 seconds. You're going to see that the population has grown to 200. So start with 100. You're going to see that after 10 seconds, 200. So now the question is, if you wait 1 minute, so let's say t equal 1 minute means what? 60 seconds. So 60 seconds, the unit has to be the same. How many bacteria are there? So that's the question. Okay, if you start with 100, if you wait 10 seconds, you're going to see 200. So the question is, if you wait 60 seconds, now what is how many you can see? Okay, so So we know that this is a exponential growth problem, and then we know the solution by the theory that we just discussed. So the so this kind of model gonna follow pt equal a constant e to the kt model. So where k is positive, that we don't know, and c also we don't know. So the goal is to use the data to find the population after 60 seconds. Okay, so let's try to use the idea here. So we know that the since p to the 0 equal 100, we can say that 100 equal p to the 0. So you're going to plug the 0 to the equation. So it is c e k to the 0. That means c. So that means this one says that c equal 100. So c equal 1. We knew that before. Remember from the graph, we knew that the starting value has to be the c value. So that means your model equation becomes pt equal 100 e to the kt. So the only thing that we don't know is k now. Okay, we still don't know k. So let's see what we can do with that. But we have one more information. We know that p to the 10. If you put 10, we know that it is 200. So we can use that data now. So that means it is 200. So that means we plug in 10. So that means it is 100 e to the k times 10. Right? So we have that. And then what we can do is we can divide both sides by 100 now. So we can divide both sides by 100. If you divide both sides by 100, what you're gonna get is you're gonna get 2 equal e to the 10k. Okay, 2 equal to 10k. Now what we can do, take natural log. So take ln, the natural log of both sides. If you take ln or natural log, what will happen? You're gonna get ln 2 equal ln e to the 10k. Okay, ln e to the 10k. But from college algebra, we know that ln e get cancelled, and this simply equals to 10k. So this is the college algebra result. Okay, ln ex. So I'm gonna write the result here. So what the result says? The result says ln e to the x equal x. Ln e to the x equal x. What's the other result? There's another result. E to the ln x is also x. Okay, so remember these two results. One is valid for any x, the top one valid for any x, the bottom one valid only for positive x, because you have ln, there's a natural log function. You have to be careful with that. Okay, so we can use the top one here. So if you use the first one, we're gonna get this. Okay, we're gonna get that. Okay, now we can solve for k. So this says that k equal ln 2 over 10. K equal ln 2 over 10. Now what we can do is we can plug in that into the equation. Okay, we can plug in that into the equation. So if you plug in that into the equation, now what will happen? Your equation simply becomes pt equal 100 e to the ln 2 over 10 times t. Okay, so and this is roughly equal to 100 e to the, if you simplify ln 2 over 10, ln 2 over 10 is around 0.69. So you can write it like that if you want. Okay, so this approximation, that's about the number of bacteria, because the reason is if you simplify ln 2 over 10, it is roughly 0.069. Okay, that's the reason. Okay, so now we know that, and now what we need to do is we need to get the model equation. So that means at t equal 60 at t equals 60 seconds, 60 seconds, the population is, so you can say P60. So let's plug in. So if you plug in the 60 here, you're gonna get 100 E 0.069 times 60. So if you simplify using a calculator, you're gonna get roughly 6400. Okay, so that's many. So that's the number of bacteria. So you're gonna see that after 1 minute, you're gonna see roughly 6400 bacteria. Okay, so this is how you do the algebra, and you can see that it's not that difficult, but you need to kind of understand what's really going on here. Okay, so I'm going to give you like a short note here. So the note is we have some terminology here. So is solution, okay, solution such as you can say such as PT equal C e to the KT is called a general solution. Is called the general solution. It's called the general solution. Okay, it's called the general solution. While PT equal 100 e to the KT is called a particular solution. Why we call it a particular solution? Because this is a special solution, because it only works for that particular one. That's why you get 100 there. So it's not general. In the general solution, you should see a constant like C sitting there. So it depends on how many derivatives we start with. You know that is the equation has only one derivative, so that means there should be one constant. Okay, good. So so this is something you can remember. Okay, so let's continue. So this is just one model. Actually there are 4 very common models that we can use. It's like it's in even in other courses you're gonna see there are 4 common models. So I'm gonna call it 4 fundamental equations. So or you can say 4 fundamental models. Okay, 4 fundamental models. 4 fundamental models. 4 fundamental models. So why we call it like that? We can see that they appear frequently. Appear frequently, and then also the other thing is worth to remember. Worth to remember. We already solved one model. Okay, we already solved one model, but there are 3 more. So let's start with the first one that we already have. What's the first one? The exponential growth. Exponential growth. So we already discussed that. Exponential growth model. Exponential growth model. So if you say y is the dependent variable, y is the dependent variable, and x is the independent variable. X is the independent variable. So we're gonna go in general. So we're gonna use y and x. Okay, so if y is the dependent variable and x is the independent variable, then we can write this equation like this. So your model equation becomes, so you can write it like this. So we can write this one as, in this case, in the exponential growth, what's gonna happen? The rate of change is proportional to the population size. Okay, so rate of change is proportional to population size. And then in other words, you can write this one as dy over dx equal ky. Okay, where we assume that k is positive, and then we just show that the solution going to be, so we can write this one as dy over dx equal kx, ky, not kx, okay, ky has a solution given by y to the x equal constant times e to the kx, where k is positive. So that's what you will remember. So if you get an equation of like this, dy over dx equal ky, then the solution is like that. So you can just take it now, okay, because we proved that that's a solution. So this is something that you want to remember. That's the first one, okay? I'm going to call equation number 1. That's equation number 1. That's the first model. So let's go to the second model. So what's the second model? So what's going to happen, it's what we call the exponential decay, okay, this exponential decay, exponential decay. So what's exponential decay? Now what's going to happen is dy over dx, the rate of change is still proportional, but it's gonna go down. So that means in this case its equation is like negative kx. The previous one was positive, but this is negative, so it's a negative ky, okay, negative ky. It's gonna decay now compared to the population size. We assume that k is still positive. So so if you look at the first one, the graph of the first one looks like this. So that's the graph of the first one. It's going to exponential growth. It's going to start with like that. It's going to grow. So this is the k equal positive situation. So let's look at this case. So in this case, you can show that from a similar argument, the general solution. Okay, so the general solution is very similar. It is yx equal c e to the negative kx. Okay, negative kx. Remember whether it's a x or y. It's a kx because x is the independent variable. So that is the solution for the second case. So that's the solution for the second model. Okay, the solution for the second model. If you have a negative sign, the negative comes. If it's a positive, the positive comes. And we still assume that k is positive. K is positive. So if you look at the graph, how the graph looks like. So this is the graph. So what's going to happen? It's just going to start with some value and it's going to grow. It's going to decay. So that's the x, whatever the independent variable, and this is the dependent variable. So you can start with c, and then you can see that it's going to grow, it's going to decay. So there is a moment it's going to get exactly half of what you had before. So you start with c, you get c half. This time is called the half-life. Okay, this time is called the half-life. How much time you're going to get? This is called the half-life. Some people use t half, but let's use t naught just to make less confusion. T naught, that's the half-life. How much it take to reduce to half of what you had before. And the same thing, you're going to get half of this. So that's the half of that. It's going to go that, and you can see that time is exactly the same as the previous one. Still t naught. So that's a c to the 4. So you can continue. So you get half of that. Okay. You can see it's still t naught. So always t naught. So that's called the half-life. Half-life. Okay, this is called half-life. Half-life. Half-life means how much time it takes to reduce to half. Okay. So yeah. So I'm going to give you a small exercise first, just to check whether this is the case. So you take the derivative and plug in. So check this. Okay, so that's something you want to try to see whether you plug in, you take the derivative and plug in and see whether it's gonna work. So now so let's talk about the half-life. Okay, just a little about the half-life concept. So what's the half-life? Half-life, how much time it takes to reduce to half-life, to the half of what you had in originally. So you can say time, you can say time taken. Okay, time taken to decay, time taken to decay, half of the material, half of the present value, half of the present quantity. We can say it like that. So how much time taken to decay or reduce, time taken to decay, half of the present quantity. Okay, that's what we call the half-life. So let's write. So I'm gonna do the calculation here. Actually, we already did the calculation. This is just like kind of little exaggeration here. So we have so we start with C, and then you can take T naught amount of time to reduce it to C and half. Okay, so C is just, we don't know, whatever C. Now we can use a formula. So our formula is what was the formula? So we use Y here. Okay, so it's Y. So so what we have is Y equals CE minus KT. So if you plug into that equation, so new value we see half, original value we see e to the negative k, how much time it can take, T naught amount of time. Now what we can do, we can simplify this. How to simplify? You can cancel C from both sides. Okay, if you cancel C from both sides, you're gonna get 1/2 equal e to the kt naught negative. Now what we can do is we can flip this over. So if you flip this over, this become 2 and this become e to the kt naught. So right, if you flip over, if you flip 1/2 become 2, and then e to the negative kt naught become e to the kt. Now what we do, we can take the natural log of both sides. So if you take the natural log of both sides, this become ln 2, this become ln 2 equal ln e to the kt naught. As before, this simply become kt naught. So from that you can say that the k is ln 2 divided by t naught. So that is the k value. Okay, so after you get the k value, now you can plug in that into the equation. So if you plug it into the equation, your equation simply become yx equal c, as a constant, e to the negative ln 2 over t naught times x. Okay. So that is the equation. This will be useful not in my class, but for like other classes such as physics and chemistry and biology, because they can use this equation. This is a half-life equation, but they normally replace x by t. So instead of x, they're gonna use t. Okay, that's okay, whatever, but that's the equation. So this will be useful for some other classes. Good. So that's the second model. So let's talk about the third model. Okay, third model. So we already discussed two. We already discussed the so if you go back, so we discussed the exponential growth, and if you look at the exponential growth, you can see that the equation is this one: dy over dx equal ky, has a general solution yx equal ce kx. And then we talk about the exponential decay. Only difference is k now become minus k. So that means your new solution is, so your differential equation is dy over dx equal negative ky. The corresponding solution is yx equal ce negative kx. That's the solution. And then we have the third one now. Okay, so so the third one is what we call the simple harmonic motion. So that's the third case. So it's number 3, the simple harmonic motion. Simple harmonic motion. Okay, simple harmonic motion. Some people call SHM. Okay, simple harmonic motion. So so this kind of one has a second order differential equation. So we have a second order differential equation. Second order differential equation. So it is d squared y over dx squared equal negative k squared, you can say y. So that is the equation that you're going to get with k positive. Okay, so see the terms that we have. So it's d squared y over dx squared equal negative k squared y. So only thing is, compared to the previous one was, if you look at the previous second case, now we have second derivative. Okay, so if you have this kind of differential equation, so what's going to happen is the general solution. So the general solution has a form like this. General solution is y to the x equal a constant cosine kx. Remember, if it's k squared, k gonna go there, plus c2 sine kx. So that is how the general equation looks like. Okay, that's the general equation looks like. So you can remember this one for the moment. We actually gonna derive this one in chapter 3 later. So for the moment you can remember this, where this is coming from. It's kind of interesting where those sine cosine coming from. Yeah, and then so let's look at the situation. If you look at the graph of this function, but you can see that if you have a equation like that, this kind of equation always you can write like this form: a either sine or cosine. I'm going to say cosine, and then kx plus a another constant. You can bring this into this form. So this is a nice exercise, you know how to do that. So I'm going to ask you how to show that this is gonna simplifies to this. So this is a I'm going to call it exercise. Okay, so try this. How to show that this equation is equivalent to a cosine kx plus b. So because of that, you can see that this is just an exponential function. So right, so that means the corresponding graph of this function has the exponential format. So it can start with some value, and then so it's gonna go in a harmonic motion, sine cosine. Okay, so this motion is like very common. This is one of the most common motion in the nature. Okay, all our cells gonna kind of fluctuate like that. All the electromagnetic waves gonna go in this kind of motion. So because electromagnetic waves gonna follow sine cosine functions. So this is everywhere pretty much. And also, like another example is, like, let's say you have a spring and you have a mass, and then let's say you put this in a frictionless place, and then you like kind of put just a little push to this and release, and you can see that this can go in a simple harmonic motion like that. So you see that it's very common. Okay, so it's pretty much everywhere. So these are just few examples where you can have this kind of situation. So that's why this is one of the most common models. Okay, one of the most common models. So let's do an interesting observation. Let's show that this is the case. Okay, so what I'm gonna do, we're gonna prove. Okay, so let's prove that you're gonna get this is actually the solution. So how to show that this is a solution? You take the second derivative and plug in and see whether it's gonna work. Okay, so that's exactly what I'm gonna do. So let's take the second derivative. So start with the equation and take the derivatives and plug in. So how to verify? Okay, how to verify? So we can start with the equation. So y equal c1 cosine kx plus c2 sine kx. Now we take the derivative. So the first derivative, if you take the first derivative, it is negative c1k sine kx plus c2k cosine kx. That's first derivative. Actually what you need is a second derivative, so we're going to go one more derivative. So let's take derivative again, so you get one more case. So c1k squared cosine kx, this is by the chain rule, okay, minus, it's a cosine minus, so what's going to happen, c2k squared sine kx. Okay, so this is clear, this is from the chain rule. Okay, so chain rule now so what you can see is, you can see the negative k squared is common, so I'm going to take it out. If you take it out, you're going to get c1 cosine kx plus c2 sine kx. Anyone see anything? What do you see? What is this? What is this expression? This expression is simply y. So that means what's going to happen now, this simply equals to negative k squared y. So that's exactly what you want. Okay, so that means if you look at the second derivative, it's simply you're gonna get negative k squared y. Okay, so yes, so you verify that that's a solution, but verification is not important, because I mean it's important, but that's not the best thing that you can do, because sometimes what happens, you don't know, I mean, where this is coming from, where those sine cosine coming from. So that means you need to know how to solve this one. Actually we can do that, we can do that later. We're gonna use complex numbers, and we derive this formula, and you can see that this sine and cosine nicely pops up in the equation. Okay, so yeah, we need to wait maybe 2-3 weeks for that. Okay, so so one observation, so it is that since the equation, differential equation is a second order, okay, second order differential equation, second order, it is second order. There are two unknown, so there are two constants, or unknown, there are two constants. Okay, there are two constants, there are two constants, there are two. It's very important. That's equal to the order of the equation. How many derivatives you have? There are two derivatives. Okay, the second derivative. So there are two constants in the general solution, in the general solution. So remember that the order tells you how many constants. So if it's a third order differential equation, you need three constants. If it's a second order, you need two constants. If it's a first order, you need only one constant. Okay, good. So let's talk about the last type. So the last type is, what we're going to do, we're going to combine the first two types. If you combine the exponential growth and exponential decay, you get the fourth model. Okay, that's what we call hybrid. Exponential growth, and decay, exponential growth and decay model. Okay. So what happened in this case, you're going to see both. You're going to see exponential growth and exponential decay at the same time. Okay, it's kind of interesting. So the differential equation looks like this. It is d squared y over dx squared equal k squared, but now it is positive. So you remember last time it was negative, k is still positive. Last time you had a negative sign, now we have a positive sign. Okay, that's the difference. So again, this is second order. Okay, so this is a second order differential equation. So this is a second order differential equation, meaning that has two constants. Okay, has two constants in the general solution. Now, what it looks like. So the general equation is, so let's try general equation, general solution. Okay, so the general solution so the general solution is this. It is yx equal, I told you it's a hybrid, so we have both. We have c1 e to the kx plus c2 e to the negative kx. Okay, we use c1 and c2. So and k is positive. K has to be positive. So that is the solution of the third case. The fourth case. Okay, it's a hybrid, exponential, and decay. Okay, so you can see that the first part is the exponential growth part. This is the exponential growth part with some c1 value. It's going to grow, and the second part is exponential decay part. Okay, so start with some c2 value and it's going to decay. So if you combine these two, if you add them, you're going to end up with a what we call this hybrid model. So it's at both. Okay, so that means you're going to start with some value, it's going to go down and it's going to come back. Okay, that's what happened. So if you sum these two, so what's going to happen is start with a value and then it's going to go down and come back. Okay, so that's what happened. So these kind of things are like, kind of common. So this is the exponential growth part. This is the exponential decay part. Okay, one is exponential growth, the other one is exponential decay. So that's an interesting one. This is another form. Okay, this is another form. I'm going to write the form and then we're going to see where it's coming from. This solution is another form. So another form. Okay, another form of the solution. The other form is what we call yx equal c1 cos kx plus c2 sin kx. So this is what we call hyperbolic trigonometric functions. Hyperbolic trigonometry, cos and sin. Okay, it's called cos and sin. So and again k is positive. So this is another way to write the same solution, and we can show that they are equivalent. You can get one from the other, but you need about hyperbolic functions, hyperbolic trigonometric functions for that. So so these are what we call hyperbolic trigonometric functions, hyperbolic trig functions. So hyperbolic sine and cosine. Okay, hyperbolic sine and cosine. The only part is you just add a h to mean the hyperbolic sine and cosine. So let's try to kind of talk about just a little bit about these hyperbolic functions before we move on. So hyperbolic trig functions, hyperbolic trig functions, hyperbolic trig functions. So let's go with the definition. So how to define the cos function? The cos x is simply e to the x plus e to the minus x divided by 2. So that's the difference of the cos. And the hyperbolic sine is ex, only change is a minus sign, minus e minus x over 2. That's the hyperbolic sine. So it's hyperbolic cos and hyperbolic sine. So it's worth remembering this. So hyperbolic cosine and this is hyperbolic sine. Hyperbolic cosine, hyperbolic sine. So let's talk about a few properties of this one, and I'm going to also talk about the graph of this one. So what are the few things that we can see? So for example, so let's say properties. So what's going to happen? So the first property, what is cos 0? Cos 0. If you plug in 0, what do you get? If you plug in 0, you're going to get e to the 0 and plus e to the 0, that means 1. So 1 1, that means 2 divided by 2, that means you're going to get 1. So this is exactly similar to cosine. Cosine 0 is 1. Okay, and then what is hyperbolic sine 0? The same thing. If you plug in 0, what happened? E to the 0, e to the 0, that means 1. So 1 minus 1 is 0, divided by 2 is 0. So you can see that this is equivalent to the sine cosine situation. And remember the Pythagorean identity. Now this has a different version of that. So what is happened here? So it is the, so what happened now for the Pythagorean identities? You can see that this is cos squared x, not a plus sign but have a minus sign, minus sin squared x equal 1. Okay, so why don't you prove it? So it's not that difficult. You just need to plug in and simplify. So so I'm going to say prove. Okay, so prove this. Okay, prove. So what else? So we have the common value 0. What happened to the 0? And Pythagorean identity has a different version. It's a minus sign. So let's talk about the derivatives. Okay, let's talk about the derivatives of these two. What about the derivatives? So the derivative. So let's go for the derivative. So we have d by dx cos x. So what do? You're going to use the definition. What's the definition? It is ex plus e to the minus x over 2. So that means just take the derivative. If you take the derivative of ex, it is ex. If you take the derivative of the second term, it's a minus sign, so it's a minus e to the minus x. That's the derivative of the second term over 2. But what is this? You can see that this is exactly the hyperbolic sine sin x. Okay, so this is slightly different from the regular calculus property, regular trigonometry property, because we know that if you take the derivative of the cosine, it's a negative sign, but not with hyperbolic. Hyperbolic you get the positive sign. So that's the major difference here. So we can say it's a plus sign. I'm going to exaggerate that. So it's a plus sign. In calculus, in trigonometry, basic trigonometry, you're going to get the positive, negative sign, but you have positive sign here. Okay, so and then let's do the same thing with the cos sin function. So sin x, which is d by dx ex minus e minus x over 2. Okay, and you can see that if you take the derivative, it is ex. And if you take the derivative of the second function, there's another minus sign, so minus minus become plus. So e to the minus x over 2, which is cos. So this is equal to the equivalent to the regular one. Okay, so those are the two results. If you take the derivative, you get both positive. You get both positive. Okay, and let's look at the graph of those two. What is the shape of the graph? So the graphs. Okay, graphs. So let's look at the cos. So cos x, which is ex plus e minus x over 2. So that means what you need to do is you need to graph two functions and then take the sum of the average of those two. So let's see that. So that means so we have these two functions. So we have ex, and that's the ex, and then we have e to the minus. What's the graph of e to the minus x? That's going to decay, right? So it's going to flip over the y-axis. Okay. So because you're going to change the x, so if you change the x, it's a flip over the y-axis. So that means it's going to go like that. So that's the e to the negative x. Now what do you want to do? You want to take the average of the two functions. So so what's the average of those two? So you can see that you're gonna, for example, you can evaluate at 0. If you evaluate at 0, you exactly want, that means it's going to go through that point, and then what's going to happen? this side is gonna grow like that, and this side is gonna grow like this. Okay, so good. So that's the graph of the functions. That's the cost graph. Okay, that's the cost graph. So good. And then hyperbolic sine. So this is a hyperbolic cosine. Let's look at the hyperbolic sine also. So it is sin x, which is ex minus e minus x over 2. So we do the same trick here. So I'm going to graph those two first. So this is the ex, and then e to the negative x, but you have to flip it over. So if you flip it over, so it's gonna go like that. Okay, actually it didn't come good, so it can go like that. So I'm gonna erase that part. Yeah. So so what happened? So so it's gonna go like this. Okay, like that. So this is the ex, and that is the negative e negative x. Now what you can do? You can take the average of those two. Once you take the average of those two, what's going to happen? It's going to go closer to that, and then go like that, and then go like this. Okay, so that's the sin function, the red one. It's a sin function. That's the cost function. Good. Okay. Good. So, and then you can see that these kind of graphs are like very common in the nature. So for example, let's see some applications. So I'm going to say applications. Applications. So for example, if you hang a, let's say, heavy wire or the electric cables. Okay, so if you hang a heavy wire, so what's going to happen? What's the shape of the wire you're going to get? So if you say electric poles, those are poles, and then you have an electric wire. What's the shape of that? And you can see that it's gonna go in a hyperbolic curve. These are not parabolas. It's gonna go in a hyperbolic curve. Okay, so this is a hanging wire or a cable. So they follow a hyperbolic curve. And there are other things also. So there are some natural, not natural, like there are man-made structures that follow these graphs. So so let's look at one such situation. For example, these three actually. So you can see that. So if you have a hanging wire, or in this case hanging cable, hanging chain, is exactly follow a hyperbolic cosine function. It's very interesting. But if it is not heavy, it's gonna be follow a parabola. But if it is heavy, it's gonna follow a hyperbola. Okay, so it's interesting. So it's a what I'm gonna say, heavy cable. Okay, so heavy cable. If you have a heavy cable, they're gonna follow a hyperbolic curve. And if it is not heavy, they're gonna go in a parabola. Okay, so not heavy, or very light, they are going in a parabola. Okay, so parabola. So the curve gonna be a parabola if it's not heavy. But if it's heavy, they're gonna be hyperbolas. You can prove that. What we can do, we can write a differential equation for that, and we can solve it. And once you solve the differential equation, you end up with a hyperbolic cos function. So that's the reason. Okay, you end up with hyperbolic cos function. And the same thing, because there's an arc called gateway arc in St. Louis. gateway arc. So the gateway arc in St. Louis, so which is also made using the same argument, because this is heavy. So what's going to happen is so this is going to be a the same thing, follow a hyperbolic equation, hyperbolic cosine equation. Okay, so this is like, you know, natural, not natural, actually it's a natural phenomenon, but we use that to in engineering to make sure that those structures are safe, because if you try to make it a parabola, it's gonna break down. Okay, it's not stable. So it's only stable if it is a hyperbolic curve. Okay, so that's the one of the situation where we use mathematics to solve certain problems. It's interesting, you know, how you can help mathematics to solve problems. Okay, good. Now what I'm going to do, I'm going to summarize what we have so far, and then we're going to solve one more problem from that. So let's summarize. Okay, good. So summary. Okay, summary. So we had the first equation, which is dy over dx equal ky. So if you have that equation, your solution is so what was the solution? Your solution is yx equal e to the kx. Okay, yeah, k is positive. That's the first one, which has a graph like that. This is what we call exponential growth, k positive. And then the second one is what happened here is there's a second model, which is dy over dx equal, only change is negative sign, put a negative sign. So the solution is yx equal e to the negative, oops, actually I forgot the constant, so I'm going to erase this a little. Let's add the constant, because we are adding the general solutions. This is c e kx, this is c e negative kx. We assume that k is positive because we explicitly put the negative sign there. The third, okay, in that case the graph is the exponential decay graph, so it's gonna start with the value and it's gonna go down. Okay, it's gonna go down. Good. And then the third one is the simple harmonic motion. So it is d squared y over dx squared equal negative k squared y. Okay, so this has a solution yx equal a cosine kx plus b sine kx. So we use a and b because you can see that we can do this problem in several different ways, and then every time we use a b, so it's easy. Okay, just you can put anything, it doesn't matter. And then we talk about the how the graph looks like. So this is a simple harmonic motion, so you start with the value and then gonna follow just a sine cosine function. Okay, so that's a simple harmonic motion. And then the last one, it was the hybrid model, so which is d squared y over dx squared equal k squared y. Only change is we have a positive sign. So there are two answers for this. So we have one, fx equal a constant e to the kx plus another constant e to the negative kx. That's one way to do it. Or, and we talk about there are two solutions. So yx equal or hyperbolic function. So a constant cos kx and then plus a constant sin kx. Okay, this a from the first one and the a from the second one are not the same. I just pick a constant. Okay, so if you don't like a, just put something else. So this is the summary of all the equations. So there are 4 different models, and these are the general solutions. So you can use, if you see the equation like that, you can directly use this equation. Okay, so please remember this one. This is very useful. So before we do a problem, let's try to prove that they are the same in the last model. let's show that they are the same. Okay, so how to show that? We can say that the two solutions of the model 4 are the same, or are the same or equivalent. Okay, or you can say equivalent. Okay, equivalent. So it is yx equal a cos kx plus b sin kx. Now what we can do, we can use the definition of cosine sin. So what's the cos? It is e to the kx plus e to the minus kx over 2 plus b e to the kx minus e to the minus kx over 2. Now what we're going to do, we're going to isolate the e to the kx terms and e to the minus kx terms. If you isolate e to the kx terms, what do you get? You get half of a plus half of b, so that is half of a plus b e to the kx, and then plus if you isolate the e to the negative kx terms, you get half of a minus half of b. So if you take half out, a minus b e to the kx, e to the negative kx. Now what we're going to do, you can see that in mathematics we try to make life much easier. So I'm going to call this whole term, it is just a constant. See, just a constant. So you can just call this is c. Okay, I'm going to call this is c, and then I'm going to call this is d, or even you can just call a. It's just a number. Okay, by a based on notation you can call this a and b. That's okay. But if you don't want to do that, then you can just call this c. So that means it becomes c a constant e to the kx plus a constant e to the negative kx. You can see that you get the other form. See, that's exactly that one. Okay, but just use sum. So this a and a in one form has nothing to do with the a in the other one. Okay, just a number. Okay, just a number. So this is how you can show that those two are equivalent. So you can derive from one. You can get one from the other. Okay, so let's just do one example before we conclude this section. So let's do one example to show you how to use these models. Okay, so if you see this equation, you can directly use the formula. So let's say solve. Let's say d squared x over dt squared equal negative 4x. Okay, you can see that this has the exact same format with x0 equal 4 and x prime 0 equal, let's say 2, something like that. And if you get a problem like that, what are you going to do? You're going to match with the format, and you can see that this is one of the four. So this is the simple harmonic motion. So what we can do, so in this case, so let's say, so the answer, so we can see that the k squared equal 4. So this says that the k equal 2, because we know that it has to be positive. Now we can write the model equation. So the model equation is simply xt equal a cosine k equal 2, so it is a 2, independent variable is t now, plus b sine 2t. So you can directly write this, okay, because you know the four formulas. If you go backward, you can see those are the four that you want to remember. Okay, so those are the four formulas. So this is one of them. This is the third one. Okay, it's the third one. Good. But we need the derivative here, so I'm going to take the derivative as well. So the derivative of this one is negative 2a sine 2t plus, if you do the derivative, 2b cosine 2t. Okay, now what's going to happen? We use the condition. Okay, so we use the condition. Okay, so if you use the conditions, then what's going to happen? X to the 0 equal a cosine you plug in 0 plus b sine 0. That's the first condition, but it says that this is equal to 4. So let's plug in the values, but we know that cosine 0 is 1, sine 0 is 0, and this can give you what? This term is going to go, this is going to get a, so a equal 4. That's what you get. Now let's go to the second equation. Second equation says y x prime 0 equal negative 2a sine 0 plus 2b cosine 0, but this is equal to what? It's equal to 2, as it says. Now again, as before, this is equal to 1, this is equal to 0, and this says that 2b equal 2. In other words, b equal 1. Okay, so we get all the numbers we need. So then the solution to the problem, this is what we normally call the initial value problem, IVP, initial value problem, but we're going to focus on this later more. Okay, this is just the introduction. So we're going to plug in. So it is xt equal a equal 4. So it is 4 cosine 2t plus b equal 1. So sine 2t. So that is the solution of the initial value problem. Initial value problem means a differential equation and the initial conditions. Okay, so if you have a differential equation and the initial conditions, you call this is a initial value problem. Okay, so you have a differential equation and the initial condition. These are the initial conditions. You can see initial conditions and a differential equation. Once you combine those two, you call this is a initial value problem. Okay, differential equation and initial conditions, you call a initial value problem. Okay, so this is the end of this section. I hope you learned something. Thank you.